Okay, so in the next 10 minutes or so, let's go through and try to get rid of a bunch of terms so that we can simplify this down. And as far as I get, let's see what's on the, I think on the last page here. Yeah, so I'm not sure I'll get through all of it, but eventually what we're going to do is go from the equations we just derived here, right, which you wrote out. Let's see, there should be, yeah, you wrote all that out. We're going to get to equations for the boundary layer that look like this. Right, so this is our end goal. And I'll kind of show you how we get there. So back up here. All right, so the idea here for boundary layer simplifications is that we can look at each of these terms in our governing equations and do what's called an order of magnitude analysis. All right, so we're going to look at the term and say, is this term, by just looking at the components of this and looking at the velocities in the problem and things like that, are each of these terms, is the order of each of these terms about the same as each other, or is maybe one of the terms really, really small compared to the other term? If it's really small compared to the other term, then you can just throw it away, right? Then we can neglect it and we can simplify down our equations further. Okay, so we're going to start again with the easiest one, the continuity equation. And as we're going through this, let's keep in mind a few things that we talked about last time, right? So we have this boundary layer that I've drawn over here. We have X and Y, and then in the Y direction, we do have some small velocity, right? It's U infinity is our X direction velocity. That's usually the big velocity. In Y, though, we do have some small velocity just due to the conservation of mass, right? You have to, if X is changing, it has to correspond to some small change in Y. So we'll call that velocity V sub delta in our subsequent analysis here. A couple other things to point out. So just remembering from last time, what we went through the boundary layer thickness model, we said delta M over X is approximately equal to 2 over the square root of the Reynolds number. So delta T over X is approximately equal to 2 over square root of Reynolds times Prandtl. Right, those were our solutions from last time. This is an X. And we also made the observation that delta M and delta T are typically much smaller than the length L. Right, so this here being L in the problem. Right, typically the boundary layer thickness is going to be much less than the overall length scale of the problem we're talking about. And that's really important when we talk about simplifying these things down. What's the other thing we want to know? So normally Reynolds number is also much bigger than 1. So a normal Reynolds number is going to be thousands, hundreds of thousands, right? That's a normal Reynolds number. Okay, so let's go through and do our order analysis here. So what we do is first, let's say we're going to take each of these terms, right? This term here and this term here. And I want to see if we can neglect either of those terms. So to do that, we write out, just to be pedantic about it, we write O. So O is the order. And we're going to look at the order of the du dx term. And we're going to compare that to the order of dv dy. Right? So we don't care so much about like preserving signs and coefficients and things like that. We're looking at, is the order of those two things about the same? For this equation, well, yeah, like they have to be, right? That what's happening on the left-hand side has to be exactly mirrored on the right-hand side. They're equal to each other by just a difference of a sign. So the order of both of those things has to be exactly the same. Right? And so if we kind of look through what the actual order would be, well, what's the order of du dx? What's the biggest that u could be, or what's the biggest that du could be? U infinity, right? What's the biggest that dx could be in this problem? L, right? So the order of du dx is u infinity over L. That's a good approximate order for that derivative, right? Let's look at the y term. So what's the y could be, what's the velocity we're calling in the y direction? We call that v sub delta. V sub delta. So v sub delta is our y-directed velocity, and what's our biggest y dimension in this problem? Delta, yep. So delta. So we know, now we know that delta is small and L is big, right? So if we know that's true, what does that say about the relationship between U infinity and V sub delta? V sub delta has to be really small, right? Just by the math here, it just is telling us that. Okay, so, and in fact, if we wanted to kind of go through and solve for this, we would say, okay, U infinity over L is approximately the same as V sub delta over delta. So if we solve for V sub delta, we would see that V sub, losing track of my Greek symbols, V sub delta is approximately delta divided by L times U infinity. Right, so that velocity is scaling by that ratio of the boundary layer thickness to the overall problem. So normally that's going to be a really small velocity, right? Makes sense. Okay, let's keep moving here in the last, I think we'll get through probably, yeah, we'll get through the momentum one, and then probably what I'll do is leave the Y momentum and the energy for next time. So let's get through the X momentum first. All right, so here's our governing equation that we derived. So what we want to do is look at each of these individual terms, right? This term here, this term, right? Each of these 5 terms, we're going to look through the order of those terms and see which of them are big relative to the others. So let's start with the first term over here. So we have rho u times du dx. So what's that order of magnitude? That would be, let's just write it over here. It would be rho times u times what's u, so sorry, rho times u infinity divided by L, right? So rho u infinity squared divided by L is about the order of that first term. Okay, we look at all these things, U infinity, L, rho, those are all, non-zero numbers. Like it's likely that term is going to stick around. It's kind of an important term. So let's look at the second one here. So what's the order of the second one is going to be, again, rho. So what's our V velocity? That's V sub delta. And then our U velocity, U infinity, divided by delta. So that's about the order of that second one. Okay, remember though that so V sub delta, we said V sub delta is approximately delta over L times U infinity. Sorry, that's really messy. Let me clean that up. So we said V sub delta is approximately delta divided by L times U infinity. So keep that in mind as we're looking at how that term scales, with that second term here. So if we make that substitution for V sub delta, we end up with actually rho times U infinity squared divided by L for that second term. Okay, so again, now that's exactly the same thing as the first term, right? So at least between those two terms, we can't get rid of either of them. Okay, so let's look here at the third term. So third term is going to be, let's see, dp dx. So dp dx is going to be what's the largest pressure that could be exerted, or what's the largest pressure gradient that could be exerted. It's going to be in proportion to the momentum of the fluid that's coming in, right? So this particular term ends up being, again, rho u infinity squared divided by L. That one's a little harder to see, but that's the largest pressure gradient that you could have across that differential control volume. Okay, so this term here, we end up with, mu times u infinity divided by, so delta, so the gradient du dy, right? That's going to be u infinity over delta, du dy. But that gradient, then the derivative of that gradient is u infinity over delta squared. So we have mu u infinity over delta squared for that particular term. This is a mu. Okay, and this one ends up being mu times u infinity over L squared, second derivative, puts a squared in the denominator there. Okay, so let's look at these terms. We have a bunch of stuff there. These first three things here, let me just circle them. So this one, this one, this one all have the same magnitude, right? The last two are kind of the ones in question. So let's call these here, I realize I'm like a minute over, sorry about that. So let's call this 1. The value of this is about 1. So then what's the value of the last two? Actually, I have to stop there. So we'll pick this up next time. We'll get through and we'll figure out whether those last two terms can be canceled. Okay, thanks everyone.